Okay, here I am back again to complete what I didn't do in the last session. I thought it'd be real quick, but I got to pontificating, and so here we are. Now let's continue on specifically with the lighting of your layout, not the LED lighting of buildings, street lights, passenger cars. I'm talking about creating skylight and sunlight. Let's do it. Okay, now let's talk about light. This is really the subject matter of most interest, not how I built a stand frame, so I could roll it around in my space here, in my workshop, in my studio. So let's look at the light in this image. Denver, Rio Grande Western, there are several elements of light in play here. There's sunlight. How do we know there's sunlight? We know there's sunlight because there's shadows. And there's skylight. How do we know there's skylight? Because the shadows aren't black. So sunlight is direct light, and skylight is a diffuse light source, and you know what the diffuse light is by looking in the shadow. If you can see objects in the shadow, then there is light that is entering the shadowed area, and it lights up the objects in the shadow. That's diffuse light. That comes from skylight. If you went outside and stood in a shadow, so you were completely in the shadow of something, and then looked down at your pants, your shirt, your hands, your shoes, the illumination for those objects is coming from scattered sunlight from the atmosphere. And the reason that the sky is blue, and I know this is sophomoric, but I'll run it by everybody anyway, is because sunlight, the shorter wavelengths, which means the more red ones, they are not scattered like the blue light is. When you look up at a portion of the sky that's blue, what you're seeing is the blue part of the spectrum from the sunlight that's been diffused, and it's going out in all directions. So the shadows are always lit by the skylight. If you're going to create a natural looking light for your layout, you need shadows, and you don't want the shadows to be black. You want some light lighting up what's in the shadow. So to do that, we're going to have two different light sources for our layout. We're going to have some diffuse light, which needs to be very even. Picture it like this. Let's say you were standing in a great big dome, like a bowl, and that the inside surface of the dome was lit completely in all 180 degrees all the way around you, all the size tops, everything. Any object inside of there would be evenly lit all the way around, and there'd be no shadows. Now, if you introduced a opening in that dome for sunlight to come in, now you would have shadows. So picture the light from the skylight is coming from every direction. That's why there's no shadow. Okay, now let's consider light for your layout. Put a layout outside, that would be nice. As a matter of fact, when I moved this layout from the location at Trevor's house, who was finishing the train, over to my house an hour away, we momentarily moved it into the sunlight as we put it in the truck. And everybody kind of looked at it and goes, wow, that looks really good in sunlight. The lighting is everything really for your layout. Think about this. If you're looking around you, you do not see objects. You see light. Put yourself in a room where there's no windows, nothing but electric light. Look around you at all the objects, then turn out the light. Do you still see the objects? No. Are the objects still there? Yes. What's missing? The light. So all that your eye sees is light. Again, you may think that's sophomoric, but when you're considering the science of light and the interaction of light with matter, you need to be within that realm completely in your head when you're deciding what you want to do. The light that you use is extremely important. So electric light. Well, obviously there's the incandescent light. We're all familiar with that. And notice that this incandescent light, look at the temperature of the filament in Kelvin. That's 2,700 degrees Kelvin. That is warm white. So if you go to the store to buy yourself a light bulb or a fluorescent light or LED light, They are rated in temperature in Kelvin. 2700 is about the lowest, and that's a warm white. Typically, incandescents are warm white because it is thermal. Now, if you notice a little jaggedness on the curve, that is an indication of the 60 hertz, 60 cycles per second power that's lighting up that light bulb. And notice that that light bulb does not get up to full temperature and brightness until well after 0.6 of a second. So 600 milliseconds, more than half a second. So it's taking more than half a second. Well, actually, it looks like it hits full at about 0.4. Let me back up on that. If you get up to 0.4 seconds, that's just under half a second, you're pretty much at full luminance. And then, of course, look when they turn the power off. You see how that slope decays? It drops real quickly at first as the filament cools, and then it starts to curve off. And that curve actually goes on for a long ways before it gets all the way back to room temperature. My point is, incandescent light bulbs have thermal inertia. And that thermal inertia is the reason you don't see it flickering. Now, there's another thing that keeps you from seeing it flickering, and that's something called persistence of vision. And that is the rods and cones on your retina cannot respond at 120 changes per second. So if you have 60 cycles, that means that the current is running in one direction for a 60th of a second, well, actually 120th of a second, and then the other direction for 120th of a second. That's a full cycle, 60 of them per second. So that means that the power to that bulb is going on and off 120 times per second. That's that little jagged edge you see up on top of that curve. Now, your eye is not going to perceive that for two reasons. One is the change is very, very little, and the persistence of vision of your eye wouldn't let you see it anyway. So when you look at an incandescent light, it looks like it's steady at a steady rate for two reasons. One is that it has thermal inertia, and the other is your persistence of vision. Now let's consider fluorescent. Now fluorescent lights, even though you've probably never noticed it, they do flicker at 120 times per second. So there you see a 60 cycle sine wave, and then right below it you see the current. That means that the current is reversing in that fluorescent bulb 120 times a second. 60 hertz goes one way, then the other, full cycle, 60 times a second. For the current to reverse, because a fluorescent bulb basically has an ionization. So on one polarity, the current arcs from one end to the other, and then when the voltage reverses, the arc goes completely out. It completely extinguishes, and then it arcs again in the other direction. So a standard fluorescent bulb puts out 120 pulses of light per second. Your eye can't see it because of persistence of vision. Now, if you weren't really aware of that and you started working with vision systems, that means digital cameras, and you started to do, say, snapshots, and you took a series of images, you would find some of them light, some of them dark, and some of them somewhere in between, because the charge coupled device, the CCD in the digital camera, can respond at that high frequency because it does not have persistence of vision. If you're doing visual inspection systems, meaning you're using a digital camera to inspect a product and you're using fluorescent lighting, you have to use a special high frequency ballast so the camera doesn't pick up those different ranges of lighting. Fluorescent has its challenges. Incandescent has its challenges. Now LED lighting. LED lighting, and here I'm just showing a standard forward current with forward voltage. Notice that you have no real current until you hit about 2.4 or so volts. And as you steadily increase the voltage, you get steady more current. With an LED, if you increase the luminosity, the output up to a certain point, we'll say 100 of forward current, milliamps, and you leave it there, then the curve and flex over to horizontal, and it stays steady state. There's no fluctuation whatsoever. So the adjustability, if you like, of the LEDs is much better than fluorescent or incandescent. Incandescent is very nonlinear, and fluorescent, it has its challenges. So LED lighting is the best way to go to illuminate your layout. If you're going to use LEDs, I went online and I looked to see what people were doing. I already had my LED lighting done for the most part. And I thought, should I do a video or not? So I went and looked what other people were doing. I thought, well, okay, I'm going to go ahead and do it, because it doesn't appear that a lot of other people are doing the skylight, sunlight, moonlight approach that I'm taking using RGB type LEDs. So an RGB LED, and this is an SMD, surface mount device. So when you see SMD, that means surface mount device. RG means red, green, blue. Red, green, and blue are the basic primary colors for light. Now, light is additive, pigment is subtractive. Let me explain that. If I add red and green together with paint, okay, go back to your childhood days when you were mixing paints and expressing your artistic nature. If you mix red and green paint together, what do you get? You get brown. Red and green paint give you a darker color, brown, because it's subtractive. It subtracts light, doesn't add it. If you mix red and green light together, like from LEDs, you get amber or yellow. Green and blue, you get cyan. Red and blue, you get magenta. Light is additive, pigment is subtractive. So you kind of have to relearn your basic primary colors. And there's different palettes. We don't want to get into all the fine details. So red, green, and blue. So what you see in front of you is a 50-50 surface mount device, RGB. There's a red LED, a green LED, and a blue LED. 50-50 is the measurement of the shape of it. It's square. So I think it's in millimeters. It's a metric measurement. And so when you look at the four numbers, when you're looking at LEDs, that defines the shape of it, the size of it. Obviously, the larger the size, the more power it can handle, it can dissipate. So RGB. There's also RGBW. That's red, green, blue, and white. So you see that yellow portion of the LED, the surface mount device, and notice there's more pins on this. That is a warm white LED, and then it's also got a red, a green, and a blue. So red, green, blue, and warm white. And the dime there gives you kind of an idea of the size. Now there's actually another higher, more convoluted product called a RGBW. It has two white LEDs and the RGB. So there's 5 LEDs, warm white, red, green, blue, and pure white. And notice that the warm white is between 3,000 and 3,200 Kelvin. The pure white is way above that. So the pure white might make everything easier to see, but it sure ain't going to look like sunlight. So you want the warm white for sunlight. You can also reproduce both of those whites with the RGB simply by how much of each spectrum, portion of the spectrum, you dial into the red, the green, and the blue. Here's that RGBW LED in a luminant state. So you see the red, the green, the blue, and then you see the warm white. Okay, now this is a different format. This is a LED strip that has RGB and white. So you see every other surface mount device is a different color. That's because it produces the whites, and the one that's kind of clear looking, that's the RGB. When it comes to powering your LED strips, you're going to see a chart like this that's going to be, should accompany the strip, either in the online documentation or with the product in it when it arrives. Now the picture down below is showing a monochrome LED strip. Notice it has 2 connections, minus and plus, and that's it. So that is a dimmable monochrome, meaning one color. It's orange, it's blue, it's yellow, it's red, it's white. It's one color, monochrome. But here's what I want you to see, that you can determine the wattage by length. Now, that depends on the density of the LEDs on the strip. So look under wattage. You see 30 LEDs per meter watts, 60 LEDs per meter watts. So notice 60 LEDs per meter give you exactly double the power consumption as that on 30. So when you're considering how big a power supply you need to tally all this up before you get too far ahead of yourself. In other words, don't buy a power supply until you've nailed down how many LED strips you're going to use. And there's some other things in play too, and I hope that I remember to bring them up later. But you can determine exactly how much power you need, what size power supply. Typically, these strips are 12 volts DC. So to determine amperage, you divide the power by the voltage. That gives you the amperage. Power divided by voltage. So power equals E times I, current times voltage. So you can transpose that around and determine any of the others. Now, these strips have little copper exposed spaces, typically every 6 inches or every 3 inches roughly along the strip, and you can cut them with scissors. So here we're looking at some connectors, and notice that you slide them under these little spring-loaded tabs, and notice that the blue goes under the blue wire, the red under the red wire, green under green, and then 12 volts. Now that's 12 volts plus, not minus. That's something very important for you to know, that it's you attach the plus side of the power supply to that particular line, the black line, or it might be white. And then the current goes through the red, the green, and the blue through the LED back to the dimmer or the power supply. And by the way, these things come in all shapes. Okay, they come in T's and L's. By the way, also notice when you close the clamp down, it's got some teeth on it that grab a hold of that strip so it doesn't pull out easy. Okay, now what we're looking at is two different sizes of LEDs. Now the upper one is a monochrome, but I don't care about that. And then the bottom one is an RGB. It's the size I wanted you to see. The upper one is 35 by 28 and the lower one is 50 by 50. So when you see 3528 SMD, that's a smaller chip size, not going to put out as much light. Also density. I mentioned density, and notice that the cutting points becomes more granulated on the higher density. So the bottom one, 144 LED devices, surface mount devices per meter, allows you to cut on every single separation between one SMD and the next. That's pretty tight though for adding it into a connector. So you look right above it, 60 LEDs, that's a much better distribution, and that gives you some space to actually put them into connectors. And then of course the 30 LEDs, that's spread out. So it's up to you to determine what kind of density you need. And if you have too much density, then you just spent more money on it than you had to, and you're going to have to use a larger power supply. Here again is a couple examples of different LED strips. Take note that the cut lines on here, see you've got plus 12 GRB. Now, why it's GRB instead of RGB? I mean, they call these things RGB, but they're all manufactured GRB or BRG, whichever way you want to say it. Now, these are two different strips here. The upper one looks like it's a combination of two different types of LEDs to give you your RGB. The second one is a combination of both. And the third one is a combination of RGB and white. See, it says L1, W1, W3, L3, and those markings are based on how it's wired between the cuttable points. The third one, though, the second one, the third one, notice that those are both RGBW or RGBWW. So the second one with the red circle on it, see, that's 12 volts, G for green, R for red, B for blue, and then WW for warm white, and then W for pure white or bright white, like more bluish, less warm. So you see you've got the RGB comes in RGB, RGBW, and RGBWW. If I were you, I don't know that I would use any of the W's. In other words, I would stick to the RGB unless, I guess if you want to spend the extra money to add the white, because that requires a separate control. When you mix red, green, and blue together, you get a hue, or some people like to call it a tint. The RGB and how you mix those with separate controls determines the color. And then if you add white, that increases the intensity. Because remember that white is made up of red, green, and blue. So if you have white, you've got the full spectrum of red, green, and blue. And then on top of that, you're adding more red or more green or more blue to give you more intense color. Okay, now as far as fastening these LED strips down, they come with a double sticky tape mounted to them, and I want to warn you, when you go to peel that back, be careful that you're not peeling off the entire double-sided tape, and so you've got nothing left on the back of the LED strip but just plain plastic, no adhesive. So be careful when you start peeling it back. Now, if you stick this to bare wood, it's going to stick, but it's not going to stay for any length of time, because as the wood goes through its hygroscopic cycles, that LED strip is going to extricate itself from that surface. So you could always, even hot melt glue is not going to stick so good. So I use these little brackets, and I actually, if I'm running dual strips, which I do for this layout, I actually get the tab on the other side of the screw to overlap onto the strip next to it, so I can use one bracket to hold down two strips. These things come in packets of 100 or 50. They're not that expensive, and I've seen a lot of people attaching their LED strips with staples. You can do that. Nothing wrong with that, stapling it down. Just be careful not to run the staple down on top of an electrical component and short it or break it. Because if you break anything on this strip, you've pretty much ruined the whole strip, unless you want to take it apart, cut out the bad part, butt up those little copper points and solder them back together. So I would plan ahead to lock down with some mechanical fastener your LED strips to your layout. That means if you've got to run screws overhead to fasten them down instead of staples, so be it. Power supplies. Now these are NEMA 1 power supplies, meaning that they're open frame. You know, they're not dust proof, they're not waterproof. They're very inexpensive. These run anywhere from $10 to $50 depending on how many amps you want. Obviously, the bigger the frame, the more current. The part number usually includes the voltage and the wattage. Now, I can't really read these. I wasn't planning on reading them. The brand is Meanwell, M-E-A-N-W-E-L-L, very common brand. And if you look close at the terminals, you've got L, N, ground, plus V, and minus V, or minus V and plus V. So it looks like they're giving you one input for line, that would be hot, one for neutral, one for ground, and then you've got two for minus and two for plus. This is just to make it easy for you to distribute. Now, they don't all give you two terminals for each for minus and plus. Some give you three each for minus and plus. But these are what the power supplies look like. Looking at these, I see a screw hole or an opening in the flange there, so you could screw it down. I would not depend on that. There are brackets that you can buy that snap into the sides that fasten these down. And of course, the shell is expanded to allow air to flow through because they will produce heat. As far as controlling the individual colors, there's two ways to go. Actually, more than two ways. The bottom dimmer, down on the bottom, look there, maximum output of current 3 amps per color. So that means the maximum current that you can run through this device is 3 amps for red, 3 amps for green, 3 amps for blue. So you look on the left side and you see plus and minus V. This can handle 12 to 24 volts in. Let me explain something to you. If you buy 12 volt LED strips, will they put out more light if you put 24 on them? Yes, they will, for about 1 second. You're going to get a lot of light, real bright for 1 second, and then they're gone, they're burned out, throw it away. So if your LEDs are 12 volts, then you need a 12 volt power supply. If it's 24 volts, then you need a 24 volt power supply. So this bottom dimmer with 3 knobs on it, you put the 12 volts in polarity-wise. That red LED will light up to show you got power. And then on the other end, the plus V goes to the common on the LED strip, which is going to be either black or white. And then you've got an RGB wires that go to the red, the green, and the blue on those LED strips. Now, if you don't have a lot of LED strip, if you've calculated, you've tallied up all of your current draws, and it's under 3 amps per color, then you use this bottom one. If you're going to have more than that, then you want to go to 3 of the upper ones. Now, the bottom one's about $10, I think, and the upper ones are about $4 to $5 a piece. So if you use the 3 upper ones, you're going to spend $15. The upper one takes up more space, and there's more wiring required. I use the upper ones that way. If I want to add more LEDs, I can go up to 8 amps per color. So the upper ones, they don't know anything about red, green, and blue. They got voltage in, voltage out. And by the way, these are pulse width modulation. Just to keep it simple, PWM, pulse width modulation. Picture somebody flicking a light switch on and off real fast. The rate that they flick it on and off stays the same, but sometimes they leave it for a length of time, they leave it on more than they have it off. The overall effect is a brighter light. Or if they leave it off more than they leave it on, then the overall is dimmer. That's what pulse width modulation is. What I did, and again, I didn't know these pictures were bad until, days later. When I go to use them in this lecture, and they're damaged. So I couldn't even use some of them at all. They were that bad. These are good enough to get by. So I cut the connectors off the LED strips, and then I put them together in a ferrule and then clamped them down to a terminal strip. Now I'm using 8 terminal strips because I didn't have any 4s. You only need 4 terminals. So I wired up 2 strips. Now you're probably thinking, well, Tim, could you have connected the other end of these 2 strips together with one of those connectors? And I have dozens of those connectors. In other words, I have 2 LED strips running the length of this board, basically 7 feet. I could have connected the white to the white, the red to the red, the green to the green, the blue to the blue on the other end, and then just had one connection on this end. The difference is that the lighting will be more even if you feed smaller sections of the LED strips. So in other words, both these LED strips are getting the exact same voltage at this end, because as you go down to the other end, as the current draw, basically you could say it's the highest at this end, so you've got the most voltage dropped over the copper, IR losses. And if you don't know much about IR losses and voltage drop, don't worry about it. Just take my word for it. The shorter the length that you apply the power to, the more even the lighting. This is another view, and you noticed how I've got the clamp, the round part under the screw, that's kind of overlapping, and that tab on this side, it's overlapping both strips, Then I've rotated it so the other side of the clamp is also holding down the strip. And I basically follow that format the full length. And here you see, and of course I didn't leave it like that. I should have retaken the picture, but at some point I loosened that up. I rotated that clamp until the other end away from the screw was actually pushing down on the strip, but the short little stubby end on this side, on the left side, it was also still holding down the strip. I think you get the point. Okay, now you can see the full length. So if you look at the red, green, blue, and common white wire, they bring in plus V, and then each strip is powered equally. In other words, I'm applying the same voltage at both ends of these two strips. Whereas if I had only applied the voltage to one strip at this end and then connected them together at the other end, then there would have been less and less voltage available as you go down through the length of the LED strip. Okay, so now I've got them attached to my dust frame on the layout. And now you see the, and I couldn't use white. I didn't have white 18 gauge. Now I didn't have to use 18 gauge, but because I'm connecting all of these LED strips in parallel, that means that the current flow through the wires at the far end of where you're looking, down at the other end, the current flow will be higher there because it will have all 8 LED strips drawing power through that wire. So I used 18 gauge, and I didn't have white, so I used yellow, but I used red, green, and blue for the others. These LED strips, or these terminal strips, are kind of out of your view when you're looking at the layout, but the LEDs themselves are definitely out of your view because they're behind those little vertical pieces of plywood. Back to my wiring. Here's the mess, and just to explain that mess a little bit, on the left end you see a red jumper bar, then an orange wire carrying that over to another jumper bar to other jumpers. Those were all of the individual feeds for all of the isolated sections of track throughout the whole layout. And you can see, looking down on the bottom side of that terminal strip, look at those white wires. You see 2 under each screw terminal. This was when I was running the layout straight up with the NCE power cab that you see laying there. And then I had that power cab's plugged into that black box there, and I have a red and a black wire going over, and I have all of one side of the track jumper together, and all the other side, that's where all the black wires and a few orange wires are going. So I'm running all of the track off of one signal, so to speak. Okay, in other words, I'm not doing occupancy detection or current sensing. Now I'm going to tidy this up eventually. That one white and blue wire that seems to wander off by itself over to the right end, that's because I ran out of terminals on this end to give each zone an individual connection all together in one spot. I will rectify that at some point. Okay, now you see I've tidied it up, and I can see I forgot to animate these highlights. So they all came on at the same time. So the first one on the upper left, now you can see that I've got, for the most part, all but one of the isolated zones rewired, re-terminated, but they're still jumpered together. Okay? And then directly to the right, I've got the black jumper, and there wasn't enough on one terminal, so I've got a few more on the other terminal strip, and that jumper's all the other side together. So I don't try to maintain isolation of all the black conductors coming back, but I do all of the other colors. Every single isolated track section has a red and a black wire going to terminal strips underneath the layout that you can't see. And then some of the black ones are daisy chained back to here. I try to maintain the isolation, but I wasn't religious about it. The multicolored wires that are on the far left, they go to individual sections. The orange and black, looking at the left, the solid orange line, that's the isolated zones, and then you've got the gray with yellow highlight. Those are the commons, if you want to call it that. And then with the orange and the black dot, those are all of the turnouts and other things that are on the layout, but primarily the turnouts. And some turnouts take 3 terminals, some take 2. The Katos take 2, and the Peko motors take 3. Now, the blue highlight with black dots, that's the lighting bus. So I've got 3 dimmers, and I've got, remember the yellow wire coming from the LED lighting up above, that was from the common, which on the strips was white. So that comes back as a yellow, and it goes to the minus side of the output of each of those dimmers. And then the plus side goes to the red, the green, and the blue back up to the LEDs. And then I've got power from the power supply right below there. You can see it. That comes up and goes into that bus bar that's got the blue highlight and the black dots. And that distributes the power plus and minus to each of those dimmers. And this is a schematic of that system. So you got 115 volts coming into a power supply. Then the power supply supplies 12 volts DC to each of those dimmers. You see in, in, in. Look at the 3 dimmers. You got in and out. So in comes 12 volts, and out comes whatever you adjusted it to. And coming out, the orange wire is the plus out. So that feeds the plus out, the plus voltage out to all 3 colors. And then the amount of current allowed through each color is regulated or controlled by the circuitry in that dimmer from the blue, the green, and the red wires coming back from that LED strip. And looking close at that LED strip, you see the orange wires connected. Now this says plus 24. I messed up. I didn't realize that it said plus 24. I just grabbed this off of the internet. For these LEDs, it'd be plus 12. Well, actually, I didn't even look real quick. Remember, there are 24 volt LED strips and 12. So make sure that you match up your power supply with what you've actually got. Okay, now this is kind of looking at what the dimmer does. So there's actually 2 images here, and I kind of grayed out the circuitry because all that we care about is that the dimmer controls the current flowing through that transistor 2N2222, and it controls the current flow through those LEDs in parallel. Picture those 4 LEDs as 4 red LEDs, or 4 green, or 4 blue, or 4 white. So you've got 1 dimmer controlling all of the red LEDs, and each LED has a resistor in series, that's the 1K ohm, because the LEDs can't handle 12 volts. They can only handle about 2 to 3 volts. So you have to dissipate the power, the additional voltage, in a dropping resistor. Now over on the far right, we have another image. Notice that we have 3 LEDs in series with a resistor going from plus 12 volts to blue to red to green. So remember those sections, and you had the 4 little copper areas where you could cut it with scissors, and then you went a certain number of LEDs, then you had another one? Well, each LED does not have its own dropping resistor. That's why you can't cut it anywhere in that strip, because there'll be 3 LEDs and a dropping resistor. So you have 3 blue with a dropping resistor, 3 red with a dropping resistor, and 3 green with a dropping resistor. Now, you don't need all these details to do LED lighting on your layout, okay? I'm just trying to cover everybody. Let's look at what the layout looks like with LED lighting on it. This is blue. So, and by the way, this is with my cell phone. Remember, my camera pooped out, my real camera. The cell phone camera, I don't consider that a real camera. It's a camera, and you have some control over, but not like you do with a good camera where you can control a number of things. For instance, the camera on my cell phone, and maybe I can change the adjustments. I'm not excited enough about it to fool with it, but it has auto adjust. So it tends to adjust the saturation time of the CCD to match the lighting. In other words, you might not know this, but the charge couple device that is the element that the lens focuses the light on to capture the image. The CCD is what captures the image. You expose it for a set length of time, and that would be like a shutter speed, and then you sequence off the voltage level of the array on the CCD. So if it's 1080p, 720p, whatever, it sequences off those bits and creates a digital image, and then it recharges, sequences it off. Your cell phone camera is going to adjust that refresh rate to give you the best image. The camera that I was using to take these pictures was fighting me every inch of the way, but I didn't have any choice. So I went ahead and used this image for the blue turned all the way up, the red and the green all the way down, okay? This is just blue. This is just green. And it's interesting that you can see more of it with just green than the just blue. The reason that you see more, so to speak, in other words, focus on any of those buildings, okay? How about that little house right in front of you? It's a little homestead. You see how you see more detail in the green than you do the blue? Or go up a little bit to the trailers in the trailer park. Or even further up to Fred's One Stop, which is just about right in the middle. It's right above the third trailer park. Look at the details on that. See, in the blue, you don't see the level of detail that you do in the green. That's because there's not as much blue in the pigment of that object. So there's more green in all of these objects than there is blue. That's why, if you have an object that is red and your light has no red, then the red is going to look like black because there was no red to reflect off of it back to your eye. So I'm just explaining what you're seeing here. So the green actually gives you quite a bit of detail, and the red is kind of mediocre in the detail. So it gives you the ability with RGB LED lighting to have all blue, all green, all red. Of course, you're not going to do that. But my point is it allows you an infinite, not infinite, but near infinite adjustability, because I think the pulse width modulation, these little inexpensive dimmers, I'm thinking it's similar to 8-bit, meaning that you get 256 levels for each. So if you went 256 times 256 times 256, that's how many different colors or hues or tints you could possibly adjust it to. Now this, I think, is my idea of Cloudy Day. Or maybe that was. I think that was Skylight. One of these is Skylight. Okay, that's Cloudy Day. Now, it looks better than that. It looks more like a cloudy day, where you've got, let's say you got real heavy cloud cover, there's no direct sunlight. Now, there will always be some direct sunlight, because even if you can look up and you don't see the sun anywhere, there is a tiny bit that is actually penetrating the cloud cover, and if you see any hint of shadows on the ground, then you've got some direct sunlight. Because if it's all diffuse, there's absolutely zero shadows. Now you'll notice there aren't any really shadows here. You might think you see some, but they're not. That's just differences in colors of the ground cover. There's no shadows. This is Cloudy Day, and this is daylight, as best that I could. The camera's not really cooperating with me. So Cloudy Day would be no direct light, and indirect light, or all diffuse light, skylight. In other words, no sunlight. If any of you experience the eclipse, the solar eclipse. Now, I happen to be in Netherlands, Colorado, up in the mountains, just south of where the full eclipse was in Wyoming. I was standing there looking around when there was the maximum solar eclipse. And this is what everything looked like. It had an odd bluish with a little bit of green tint, because that's all you're getting is the light from the sky that's been diffuse, the blue wavelengths and a little bit of green. So it's a weird lighting. So this would be skylight, and then to that, if you add sunlight, then you get shadows. Now, the one thing I forgot to do is to do an image with just the sunlight. If I did, and I turned off the skylight, then all those shadows, they'd be really dark. And the reason that they wouldn't be black is because there's light coming through the dust cover. Now, I made the dust cover out of a high thread count, light blue, flat sheet, bed sheet. Because when until I get my backdrops in there, I figured if it looks more like sky than something else, so much the better. In a later video, I'll go into more detail on the imaging. I went and quick grabbed a couple photos with my cell phone, one with the skylight and one without. So I want you to notice that in both cases I have the sunlight turned on. Unfortunately, the cell phone won't cooperate, so when you look at certain parts of the image, on the left you have just sunlight with the darker shadows, and on the right you have sunlight and skylight. So if you look underneath the bridge, you see the steam locomotive 3417 there that's just across the bridge about to the water tower. Look underneath the bridge there and see how dark the road is there, and then look over to your right and look underneath and you see that light. Now that's with the skylight turned on. Now the dust cover, those light blue sheets, cotton material, they are reflecting some of the light from the sunlight down onto the layout. That can't be avoided. There's just only so much you can do to demonstrate this stuff. But look at the river on the left and on the right. So if you look between the double girder bridge and the overhead arch bridge, you look in the river, look at the shadow of the rock that's in the water there. Look at the shadow of the pillar and the pylon and the bridge on the water, and then look over where you have skylight. So the one that's the most realistic would be to the right. Now, the shadows, the picture on the left, look at the motel, at the buildings that are the rooms, and look how dark the little porch is on the left, and then look over on the right. Over on the right, you can see that the doors are red, and you can see the porch floor. If you look at any of the shadows on the left, they're almost black, and you look at them on the right and you can see texture and objects within the shadows. So the image on the right is much more realistic than the one on the left, even though the one on the left does have some appeal to it. The point is that shadows really add texture and drama and richness to your image. So even if you're just standing there playing with your trains on your layout, your visual experience is going to be better if you have skylight and sunlight. Okay, that's enough right now on lighting for your layout. I'm not finished entirely with my lighting yet. I still have to install the moonlight. So I can adjust the RGB to get that kind of bluish light that you get from the moon. It's kind of bright white, but leans a little bit to the blue. So you just turn the intensity way down and you adjust, it looks just like moonlight. But to get shadows from the moon, it takes a little bit more effort. So I don't have a spotlight yet that I like for the moonlight. The spotlight that I'm using for sunlight is a 40 degree 2700K 120 watt spotlight, LED spotlight. 40 degrees is not enough angle of dispersion or, you know, the propagation. I want more angle because I'm not getting a real even sunlight brightness across the entire layout. And it's really impossible to duplicate the light that you'd get from the sun. because the sun is so much bigger than the earth that if you draw a diagram and you have the sun and the earth, the light coming from the sun, when it strikes the earth, you could almost say that all of the photons are traveling almost coherent or in parallel. They're not really, but so you get a very crisp shadow. And the sunlight is going to be real even because the sun is so much bigger than the earth itself. So to try to use a little spotlight to cover a great big, a 3x7 layout, it's just not going to look perfect, but it's still going to look better than nothing. And this is one of the texts that I have on light. It's light science, physics, and the visual arts. It's not the best one. The best one I had, I mailed it to myself in the Dominican Republic. In the box, I mailed 25 boxes, as a matter of fact, with stuff, and 6 or 7 of them just disappeared. Of course, we know where they went. But anyway, I've never been able to find another copy of that book on light. So I like books that don't lean so much into the math, but into the process. The math allows you to quantify things. So all science is empirical, and if you use the empirical data, then you can turn it into measurements, and then you can use math to manipulate what results you would expect. And so this is a reasonable text if you want to understand more about light. As far as LEDs go, if you don't understand light and you don't understand the spectrum and the interaction of light with matter, then I don't know if it's going to make a lot of sense or not. And it's not rocket science. It's just something that if you're interested in it, you'll pick it up. So thank you very much for watching, and have a nice day. Bye-bye.